This lesson is on finding the probability of the compound event A and B. This event, the event A and B, is a compound event because it is composed of two simple events. A is a simple event, B is a simple event. A and B form a compound event. Now, we can abbreviate this probability. We can write it as probability of A and B. The probability of A and B. Now, before we talk about the formulation involved in finding the probability of A and B, let's talk about two types of events. Let's talk about what we call independent events and what we call dependent events. Independent events are events in which the occurrence of one of the events does not affect the probability of the occurrence of the other event. Once again, independent events are events in which the occurrence of one of the events does not affect the probability of the occurrence of the other. Now, independent events, the idea of independent events is synonymous with what we call with replacement. That phrase is synonymous with the phrase independent events. For example, if we have a container of balls, we have two red balls, one blue ball, and three yellow balls. Reds, we have two, blues, we have one, yellows, we have three. If we have this type of situation, if we look at the probability of getting a blue ball, if we look at the probability of getting a blue ball, the probability of getting a blue ball would be equal to 1, since we have one blue ball in the container, over the total number of balls, which is 6. So the probability of getting a blue ball would be 1/6. Now, if we take the blue ball out, and if we take the blue ball out, if the first ball we choose is a blue ball, on the second trial, we are taking the blue ball out. So, once we take the blue ball out, if the first ball is blue, well, let's look at it before we take the blue ball out first. Before we take the blue ball out, the probability of getting a yellow ball would be 1, 2, 3. There are 3 yellow balls. We have a total of 6 balls. The probability of getting a yellow ball would be 1/2 before we take the blue ball out. Now, if the first ball we take out is blue, and we take the blue ball out, and we see that it's blue, and then after we see that the first ball is blue, we put it back into the container. This is what we call with replacement. With replacement, we take it out and we put it back in. With replacement, once again, we take it out and we put it back in. So, since we take it out and put it back in, before we take it out, the probability of getting a yellow ball is 1/2. After we take it out, because we put it back in, because we have what we call with replacement, the probability of getting a yellow ball is also 1/2. Because once we put this blue ball back in, we took it out, now we're putting it back in. Once we put it back in, we will still have a total of 10, not 10, but a total of 6. We will still have a total of 6 balls, and 3 of those balls will be yellow, which would give us a probability of getting a yellow ball of 1/2. Now, in this case, we say that getting a yellow ball and getting a blue ball are independent events. The fact that the first ball was blue, the occurrence of that event, the occurrence of getting a blue ball, the first ball was blue, did not affect the probability of the occurrence of getting a yellow ball, because we put the blue ball back in there. We had with replacement. So there were 3 yellow balls and a total of 6 balls before we took the blue ball out, and there were 3 yellow balls and a total of 6 balls after we took the blue ball out. And this was because after we took the blue ball out, we put it back in. That's what we call with replacement. If you do a probabilistic experiment with replacement, then the events are independent events. The events are independent events. Now, when you replace that blue ball in there, that means that the blue ball has another chance of being chosen. The blue ball has another chance of being chosen. So that's another way of saying that we have a situation with replacement. We can say that the first ball that we take out has a chance of being selected on the second trial, or on the third trial and the second trial, or what have you. It can be selected again. Why? Because we have put it back into the container. And as stated, that's what we call with replacement, or we can say that the events are independent. Now, for dependent events, if we have dependent events, the occurrence of one event does affect the probability of the occurrence of the other event. Once again, for dependent events, if the events are dependent, the occurrence of one of the events does affect the probability of the occurrence of the other. Once again, for dependent events, the occurrence of one of the events does affect the probability of the occurrence of the other event. Now, notice the difference between independent events and dependent events. In the case of independent events, the occurrence of one event did not affect the probability of the occurrence of the other. In the case of dependent events, the occurrence of one of the events does affect the probability of the occurrence of the other. When we have dependent events, we use the term with replacement, or the phrase with replacement. Once again, without with replacement. When we have dependent events, we use the phrase without replacement. When we have dependent events, we use the phrase without replacement. The phrase without replacement is synonymous with the phrase dependent events. In other words, for dependent events, we are going to take the blue ball out, see that it's blue, and we are not going to replace it. We're going to set it off on the side somewhere. This is why we say without replacement, dependent events. We do not replace the blue ball. The blue ball does not have another chance of being selected. It does not have another chance of being selected. So these are two different types of selection processes. We can select samples by replacing the ones, the numbers, or the persons, or what have you that we take out. We can select samples by not replacing those ones that we take out. Now, let's take a look at the same situation we had before. We had a container, we had one blue ball, two red balls, and we had 3 yellow balls. Now, this time we're doing the probabilistic experiment without replacement. We're not going to replace the blue ball once we take it out. Now, if we look at the probabilities before we take the blue ball out, before we take the blue ball out, the probability of getting a blue ball equals 1. There's one blue ball over the total, which is 6. 1/6. That's the probability of getting a blue ball before we take the blue ball out. Before we take the blue ball out, the probability of getting a yellow ball is, we have 1, 2, 3, 3 yellow balls over the total, which is 6. 3/6, which reduces to 1/2. Before we take the blue ball out, the probability of getting a red ball is 2/6, which equals 1/3. Now, watch what happens to the probabilities of getting a yellow ball and the probability of getting a red ball once the occurrence of getting once the event of getting a blue ball has occurred. Now, we're taking the blue ball out. That's what we're doing. We're taking the blue ball out. Let's say that on the first trial, we got a blue ball. We're going to do 2 trials, or pick a sample of size 2. So we closed our eyes, we reached into the container, we pulled out a ball, it was blue. Now, we take the blue ball out, and we keep it out. This is without replacement, so we don't replace the blue ball. That means that we have dependent events. Now watch what happens to the probability of getting a yellow ball. The probability of getting a yellow ball given, and that's what that slash means, given that the first ball was blue. The probability of getting a yellow ball on the second trial, given that the ball on the first trial was blue, would now be equal to 3. We still have 1, 2, 3, 3 yellow balls over 1, 2, 3, 4, 5. 3 over 5. Now, look at the probability of getting a yellow ball here. The probability of getting a yellow ball here, before we took the blue ball out, was 1/2. When the event of getting a blue ball occurred, when we took the blue ball out and saw that it was blue and didn't put it back in, the probability of getting a yellow ball changed. The probability of getting a yellow ball changed. It changed to 3/5 instead of 1/2. Now, as I said, the symbolism that we have here for dependent events is different than the symbolism for independent events. After you take the blue ball out, if you have dependent events, you say the probability of getting a yellow ball given that I've already taken a blue ball out. That's how you would read this. And it's a good idea, it would be a good idea for you to write this in your notes. The probability, this is red, the probability of getting, or we could just say, let's just say the probability of y, and y means getting a yellow ball. The probability of y, and the bar here stands for given. That's how the bar is read. The probability of getting a yellow ball given that the first ball was blue. Given that we'll say given that a blue ball has already been chosen. Once again, this is read the probability of getting a yellow ball given that the event of getting a blue ball has already occurred. So that if the event of getting a blue ball has already occurred, and we're not going to replace the blue ball, the probability of getting a yellow ball will change because you took one of the balls out of the container. So you no longer have a total of 6 balls in the container. You now have only 5 balls in the container. So your denominator of the yellow balls is no longer 6 as it was previously before you had the first trial. Now the total balls is 5, so the probability is 3 over 5. So this is what we mean by independent independent events. Now, the formulas for finding the compound probability of A and B, the formula for finding the probability of A and B is different depending upon which type of events you have. If you have independent events, which of course means that you are replacing the balls that you take out. Independent events this is with replacement. You are replacing the balls that you take out of the container with replacement. The first ball that you take out, once you take it out and look at it, you're placing it back in the container, and that ball has another chance of being selected on the second trial, the third trial, and what have you. Each time you take it out, you put it back in. Now, for independent events, the formula for the probability of A and B is this. The probability of A and B is equal to the probability of A, the simple probability of A, which is the probability of A in a single trial, times the simple probability of B, which is the probability of B in a single trial. For example, if we have that same container that we had before, we had 2 red balls, we had 1 blue ball, and we had 3 yellow balls. We had 3 yellow balls. And let's say we want to find the probability of getting a yellow ball and a red ball. Yellow, getting a yellow ball and a red ball. We'll let Y equal yellow, and we'll let R equal red. The probability of getting a yellow ball and, the key word is and here. We had or the last time. If you have or, you add the probabilities together and you subtract the intersection. This time, in the last lesson, we had or. Not in this lesson, but in the last lesson we had the word or, A or B, but now we have A and B. So we're talking about getting a yellow ball and a red ball on 2 trials. That's what we're talking about, in 2 trials. In 2 trials of reaching into the container, or a sample of size 2 is what we're choosing. We're trying to choose a sample of size 2. And we want the probability that we can get a yellow ball and a red ball. That's what we're talking about. 2 trials, a yellow ball and a red ball. So we use the formula here. We have the probability of getting a yellow and a red. We could let yellow be A and red be B, and then just substitute everything in the formula, or we can just use yellow and red just to remind us that Y stands for yellow and R stands for red. If we apply the formula, we would have the probability, the simple probability of getting a yellow ball times the simple probability of getting a red ball. Now this is the case because we are dealing with independent events. We're dealing with independent events. So this is with replacement. The ball that we take out the first time, we put it back in so that it can be chosen on the second trial. So what happens here, we simply figure out the probability of a yellow ball. The probability of getting a yellow ball, 1, 2, 3. We have 3 yellow balls over the total, which is 1, 2, 3, 4, 5, 6. That would be the probability of getting a yellow ball. That's what that is. and is times by the probability, the simple probability of getting a red ball, or the probability of getting a red ball in a single trial. So we look at the figure that we have here. We have 2 red balls. We assume that perhaps on the first trial, we reached in there, we took out a yellow ball, but we put it back in there. So that means that for the red balls, we have 2 red balls, and since we put the yellow ball back in there, we have a total of 6 balls. A total of 6 balls. So the probability of getting a yellow ball and a red ball would be equal to 3/6 times 2/6. And of course, we can reduce here, and that gives us 1/6. The probability of getting a yellow and a red ball would be equal to 1/6. Now this is the probability of getting a yellow and a red ball in 2 trials. Or if we reached in the container and we took out 2 balls in 1 trial, this would be the probability that one of the balls is yellow and one of the balls is red. Now, suppose we wanted to find out the probability that both balls are yellow. That both balls are yellow. We would simply have the probability that the first ball is yellow and the second ball is yellow. Y sub 1 being the first ball, Y sub 2 being the second ball. And that would be equal to the probability that the first ball is yellow times the probability that the second ball is yellow. Now, we're doing this experiment with replacement, so that if we take out a ball, if the first ball is yellow, we put it back in, and we shake the container up, and we choose another ball. We start from the beginning, and we choose another ball. So for the first ball, the probability is 1, 2, 3, 3 over 6. We saw the first ball, we took the ball out, it was yellow, we put it back in. So that means that the probability of getting a yellow ball on the second trial would still be 1, 2, 3, 3 over 6. And then, of course, we can reduce that and that would give us 1/4. So the probability of getting a yellow ball on both trials would be equal to 1/4. And of course, you need to take these fractions and change them into decimals and then into percents. Now, this formula can be extended to include any number of events. Any number of events. If we have 3 events, for example, probability of A and B and C, and the events are independent events, then that probability would be equal to the simple probability of A times the simple probability of B times the simple probability of C. If we have an unknown number of elements, for example, whatever the number of elements is, we can just expand the formula. That's what I'm saying here. Whatever the number of elements is, we can expand the formula to accommodate that number of elements. For example, if we have the probability of event 1 and event 2 and ... event n and a number of events, that probability would be equal to the simple probability of event 1 times the simple probability of event 2 times ... the simple probability of E sub n. So if you have independent events and you want to find the probability of event E sub 1 and E sub 2 and all of the other events, you just multiply the simple probabilities together. And that will give you your compound probability. Now, let's look at how the formula looks when you have dependent events. When you have dependent events, you're talking about doing the probabilistic experiment without replacement. Without replacement. In other words, if I have a container and if I have 2 red balls, once again, 1 blue ball, and 3 yellow balls, what I'm going to do, I'm going to reach into the container, shake the container up, reach into the container, take a ball out. If that ball is blue or whatever, I'm going to set that ball on the side. That ball will not have another chance of being chosen. It will not have another chance of being selected for my sample. I do not put it back in. If I reach in the container again, take out another ball, I do not put that ball back in. In this situation, we have dependent events. Now, if you have dependent events, the formula for finding the probability of A and B is this. The probability of A and B is equal to the probability of A times the probability of B given that A has occurred. Once again, the last part of this formula is not the probability of B over A. It's not the probability of B divided by A. But this number means the probability of B given that A has already occurred. That's what this probability here represents. Now, if we look at the example we have here, suppose we let A be getting a yellow ball. A is the event of getting a yellow ball. And suppose we let B be equal to the event of getting a blue ball. The event of getting a blue ball. Suppose we let that be B. So here, we're looking for the probability of getting A, the probability of getting a yellow ball and a blue ball. The probability of getting a yellow ball and a blue ball. That's the probability that we're looking for. Now, we said the yellow ball is A. So this is the yellow here, and this would be the blue. So we would have the probability of A, the yellow, and the blue. And of course we are saying in 2 trials, or we want a sample of size 2. And we're finding the probability that one of the balls in the sample is yellow and one of the balls in the sample is red. Not red, but blue. The probability that one of the balls in the sample is yellow and one of the balls in the sample is blue. That's what we're looking at. Now, we take the simple probability of A, which is the simple probability that have a yellow ball. That's what that represents, because we said A is the yellow ball. If we're looking at yellow balls, we have 3. This is on the first trial. We're looking at the yellow balls. We have 3. The total number of balls is 6. That's the simple probability of A, 3 over 6. We just look at the situation the way it is in the beginning to get this simple probability of A. Nothing has happened here. We're just looking at the probability of getting a yellow ball in a single trial, and that would be 3 over 6. Now, we're doing this experiment without replacement. We're doing it without replacement. So that means that on the first trial, we are taking out a ball. We are taking out a ball on the first trial. So that ball we're taking out. And we're assuming that we're not replacing that ball, because this is without replacement. So we assume that we have taken out a ball on the first trial. That's what this is saying. The probability of B given that A has occurred. So in order to figure out this probability, we actually take out a yellow ball, because we want the probability of getting a blue ball given that the event of getting a yellow ball has already occurred. So we assume that we have taken out a yellow ball to figure out this probability over here. So it's just like saying that on the first trial, we took out a ball, it was yellow. It's the same, you get the same result if you think of it that way. And we did not replace that yellow ball, but we kept it out. So now we only have a total of 5 balls in the container, because we took one out, and that's the bottom of your fraction, the total. We only have 5 balls left in the container. Now, for the top of the fraction, we get the probability of B given that A has occurred. So we want the probability now of getting a blue ball given that we have already taken a yellow ball out of the container. Now we look at the blue balls. We have 1 blue ball in the container. So the probability of getting a blue ball given that a yellow ball has already been taken out of the container would be 1/5. Now all we have to do is multiply these 2 probabilities together, and that gives us 3 over 30, which reduces to 1/10. 1/10. So the probability of A and B, the probability of getting a yellow and a blue ball in 2 trials would be 1/10. And of course we can change that into a decimal and into a percent. Now, just as with the probability formula involving independent events, the probability formula involving dependent events can be extended to include any number of events. For example, if we have dependent events, if we have 3 dependent events, events A, B, and C, this is how the formula would look. We would have the probability of A and B and C equals the probability of A times the probability of B given that A has occurred times the probability of C given that A and B have occurred, given that both A and B have occurred. And we can extend that even further to include 3 different events, 4 different events, 5 different events, and so forth. And in such a case, we would have the probability of the first event and the second event and ... the E sub n event, which means any number of events, would be equal to the probability of the first event, the simple probability of the first event, or the probability of the first event in a single trial, times the probability of the second event, given that the first event has occurred, times ... the probability of the nth event, given that the first event and the second event and the event, the n-1 event, and E sub n-1, given that those events have occurred. That would be the representation for any number of events that you would have. Now, let's review what we've done. First of all, we talked about independent and dependent events. We said that independent events were events in which the occurrence of one event does not affect the occurrence of the other event, and we call that with replacement. We said that dependent events were events in which the occurrence of one of the events does affect the probability of the occurrence of the other event, and we call that without replacement. And then we had 2 formulas. One formula for the probability of A and B, if A and B are independent, and the other formula for the probability of A and B if A and B are dependent events. If A and B are independent events, the probability of A and B equals the simple probability of A times the simple probability of B. If A and B are dependent events, then the probability of A and B equals the probability of A, the simple probability of A, times the probability of B, given